Welcome to BKW Physics. I'm Mr. McConley, and today we're going to talk about the conservation of momentum. Now there are a bunch of conservation laws in physics. One of them that you talked about as an 8th grade science student, if you went here to BKW, or most any New York State school, was the conservation of energy. Energy cannot be created or destroyed, it just changes forms. And you were fine with that. You said, okay, so if you lift something up, you're moving it, it's got kinetic energy. When you get it up to here, it's got potential energy. When you drop it, it's got kinetic again because it's moving. And you learned all about that in 8th grade. It was great. Well now, talking about momentum. Now you've just learned yesterday that momentum was mass times velocity. But what I'm saying is the momentum of a whole system is conserved. So what I mean by this is if I take ball A and ball B, and in picture number 1 here, they're traveling or they're moving towards one another. This is picture number 1. Picture number 2, they come in contact with one another. Click, clack, or whatever. Maybe they're billiard balls. I don't know what they are. But they're hitting each other right there. They're coming in contact with one another. And then in picture number 3, the outcome is going to kind of depend on the mass and the speed and the relationship between the two balls, because if A was going faster, for instance, then it would plow into B and it would move B this way. If they were going the same speed, they would just go whoop, and they would bounce off of each other. If you had a piece of Velcro between them, they might hit each other and then slide off together in one direction. And so there's all different scenarios here. I'll just draw an easy scenario where A and B now bounce off of one another. They were like the same mass, so they came in going 1 each and they left going 1 each in each direction. That's the easiest scenario. It just gives you the visualization of what's going on here. Now, when I say a system, you got to understand what a system means. A system is when you look at the situation as a whole, and in this system, we have 2 balls, and we're only concerned with those 2. So if we just keep our eyes on those 2, and we say, okay, this one's got momentum, and we can figure it out by mass times velocity, and this one's got momentum, and we can figure it out by mass times velocity, and we'll call this one number 1, and we'll call this number 2, or A and B, so you can tell them apart. Then, if I take this momentum, and I add it to this momentum, you're going to get a total momentum number, right? If I do the same thing down here, like I find the momentum of 1 here, and I find the momentum of 2 here, and I add them together, I'm going to get the exact same number. That is what the law says, conservation of momentum. Just like energy, momentum cannot be created or destroyed, and the total will remain the same in the system. Alright, so let's do an example of this, because that's the easiest way to see how it works. In our textbook, page 185, question number 5, so you know where I'm getting this information from, says there's a puck, like a hockey puck, and the hockey puck weighs 0.105 kilograms, 10th kilogram, and there's a goalie, we'll call him mass G, goalie, and the goalie weighs 75 kilograms. And someone's going to shoot the puck at the goalie. I'm not worried about the other person. I'm just going to look at my system. Remember I talked about systems. My system in this case is the puck and the goalie. I don't care about all the other peripheral stuff that's going on. I'm just looking at the puck and the goalie. So if I'm just looking at the puck and the goalie, all I need to know is the speed of the goalie and the speed of the puck beforehand. So before the 2 collide, here's what I know. Before they collide, the velocity of the puck is 48 meters per second, according to this problem. And the velocity of the goalie is, he's standing still. He's waiting for the puck. He's there in the goal, and he's trying to get ready to catch the puck, so his velocity is 0. Okay? Well, I want to know, the question is, how fast is the goalie moving after the puck hits him? In other words, he catches the puck, coming at 48 meters per second. That's a hard shot. So it's coming pretty fast. He catches the puck, and it's gonna like make him creep back, unless he like locks his skates out or something like that. But just assume he's got his skates in line like this, and he catches the puck, and it hits his, his goalie glove, and he catches it. It's gonna push him back a little bit. I don't know how fast is he gonna get pushed back. So I want to know. The question is, what's the velocity of the goalie afterwards? So after he catches it, what's the velocity of the goalie? So here's how we do this problem. And I'm going to try to just teach you a general form that'll work for all these problems. And in this case, it's probably like overkill showing you all the steps. But there will be other problems in which it'll be helpful to do the whole thing out. So here's how I always start. I say that the momentum beforehand is equal to the momentum afterwards. And when I'm talking about before and after, I'm talking about before and after what? The collision. Right. This is before and after collision. So I have two items. I have a puck, P, and I have a goalie, G. So I have the momentum of the puck and the momentum of the goalie beforehand. And I have the momentum of the puck, and I got the momentum of the goalie afterwards. Now in physics, the way we tell these two things apart is the stuff that's afterwards, we put a little whoop, 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 whoop right there. That is the universal symbol in physics for this is the thing happening afterwards. Now we just break it down one step further. Well, what does momentum mean? Back to the beginning, momentum means, everybody?
Mass times velocity.
So what you do here is you say this is the mass of the puck times the velocity of the puck. And this one's the mass of the goalie times the velocity of the goalie. And this is the mass of the puck and the velocity of the puck. And this is the mass of the goalie and the velocity of the goalie. Now some of you are like, I don't want to write all those steps. I can hear you thinking it already. Get over it. It doesn't take you that long, and it'll make sure that you get the problem right if you show all these steps. So here we go. Let's just plug in the numbers. What is the mass of the puck beforehand?
0.105.
In fact, what's the mass of the puck always?
0.105.
Yeah, that doesn't change, so I could actually fill it in over here if I want to also. The velocity of the puck beforehand was that 48 meters per second, the slap shot. Now, what's the velocity of the goalie beforehand? So what's actually going to happen to this whole term right here?
It's going to be canceled.
So I'm just going to leave it as a 0 because it's going to cancel right now. Now the velocity of the puck afterwards, I don't know that yet. That's the one I'm not sure of. And the mass of the goalie is 75. And what's the velocity of the goalie afterwards? Well, I don't know. But what do I know about these two velocities? This is the velocity of the puck afterwards and the velocity of the goalie afterwards. What do you know about them?
They're the same.
They're the same because you caught the puck. You're the goalie, you catch the puck, and now the puck and you slide backwards. So I don't know what they are, but I know that these two are the same number. Now that's a little hint on math-wise how you have to solve this. So hopefully you got some calculators out. Could someone do 0.105 times 48 for me? So we can follow along with the numbers.
5.04.
5.04. And we got, those are kilogram meter per second per unit. And then on the right-hand side, see how we have a 0.105 times v and a 75 times v? What I'm going to do, I'm just going to rewrite it. I'm going to rewrite it this way for you. I'm going to say it's 0.105 kilograms, and instead of putting velocity of p, I'm just going to call it the velocity afterwards because it's the same as this number also. And and I'm going to rename that one velocity afterwards. So what I've done is I've called the velocity of the goalie afterwards and the velocity of the puck afterwards. I just renamed them and I just called them the velocity afterwards because they're the same number. Okay, so in math, if you got this many of those and this many of those, and those are the same thing, what can you do to these two numbers?
Add.
Yeah, add them up. So that would be 75.105 kilograms times the velocity afterwards, and that's all equal to 5.04 kilogram meters per second. So I really just have one step left. I got to divide that 75.1 over to the other side, and I get, what do I get?
0.0671.
Yep. And that's in meters per second. So in reality, okay, that's a really slow speed, right? In reality, I think when you catch that puck, you're just going to lock your feet a little bit and you're not going to move at all. That's reality. But in a perfect physics world, you know, when your skates are lined up and there's like no friction, you go, it's just gonna, you're just gonna move back about that fast. Okay? So this is the way you do conservation of momentum problems for today. Physics.